Okay, guys, we are going to do 1.7 today. So the sub should give you or should have given you a classwork which goes along with these slides here today. And all we're going to do is go through them. You can take notes as you want. You can pause, you can rewind, you can do whatever you need to kind of make sure that you get this stuff. So 1.7 is on inverses, which is a lesson that I know you guys did in Algebra 2 last year, but maybe forgot a little bit. So this is a little bit of review. And we'll go a little bit further probably than you did in Algebra 2 as well, but hopefully this stuff starts to make sense a little bit into the video here. Be broken up into two videos. So first one's going to start with this warm-up. So what I want you to do is just pause the video, do the warm-up, and then resume it when you are all done. All right, so if you had paused the video here and started, you got f of g of x. That's what this first thing means right here. So we have f of g of x, right? And what that means is we're basically plugging in the g of x into the f's equation. So we're going to plug in x squared in for this x here. So it's the square root of x squared minus 4, right? Because we plugged in this into this x here. And you know, these are both perfect squares, x squared and 4, but just because it's under the square root doesn't mean that you could simplify it, right? It's the same thing as x squared minus 4 to the 1/2 power. Same thing as a square root is a 1/2 power. And you could never distribute an exponent here, so you can't break this up. This is actually as simplified as it's going to get. So you have x squared minus 4 underneath the radical. And that's it. That is f of g of x. Now it says give the domain of it. Now it said something, you know, you always want to make sure that the innermost function, that domain is true. So the innermost function, right, would be the one that goes inside the one. So g of x, the domain of this one's everything. So at that point, you're just going to evaluate the final answer and see what you have for a domain. And if you remember back from 1.1, when you have x squared underneath the radical, set it equal to 0. And you get x equals plus and minus 2, right, when you take the square root. And that's the one where we put that on the number line, if we remember that. So negative 2 and 2. And those, I'm just going to put closed circles on them. You don't necessarily have to, but just it's a reminder that they are included, right? Because if I plugged in negative 2 or 2, I get 0, and that's okay. The square root of 0 is still a number. It's not imaginary. So you can just pick some test points, but basically anything in between negative 2 and 2 is not going to work. Like, for instance, 0. If I plugged in 0, I get negative 4 under the square root, which is no good. Anything to the left and right does work because it'll give me something minus 4 that will end up with a positive number. So that's your domain right there. It's going to be negative infinity to negative 2, union 2 to infinity. And that is f of g of x. Now we're going to move on to g of f of x, which I'll do in blue. Now I'm going to plug in f of x into g of x. I'm going to plug this one into this one. So instead of x squared, it's root x minus 4 squared. And then we can simplify this, right? But this is technically the most exact definition of f of g of x that there is. Like, this is as perfect as it's going to get. When we simplify it, we kind of lose some of that, which I'll talk about in a second. But if we have a square root and we square it, we can say that it is equal to just x minus 4, right? So f of, or g of f of x is x minus 4. That's how you would want to put it on like an answer, right? However, when you think about the domain of this, right, if you looked at just x minus 4, that is a line. So the domain of that is negative infinity to infinity. It's all real numbers. However, if you looked at this, you would say, well, this one would have a domain restriction because it's the square root of x minus 4, right? You would have to say x minus 4 equals 0, and you'd say x equals 4. You could put it on a number line, but you might be able to just see it by looking at it. Values of x that you can plug into just this part have to be equal to 4 or greater than 4 to result in a positive number. So the domain of that one is 4 to infinity. And even though this one doesn't look like it has a domain restriction, it is technically this thing right here, which did. So always kind of refer to the original if you're going to look for the domain. Again, your final answer is this, g of f of x is this, but the domain of which has to be 4 to infinity, right? So that's what we're saying. The innermost function, the one that you plug in, that, whatever that had as a domain restriction still has to stay true. So if it simplifies, you still have to honor the fact that it's 4 to infinity. All right. Now, here we go. Inverses, right? They're written in this function. It doesn't mean f to the negative 1. It doesn't mean 1 over f of x. It has nothing to do with reciprocals. It's just a notation that we use. We're going to read this as f inverse of x, right? Instead of f of x, it's f inverse of x. That's basically how you read it. So it has nothing to do with reciprocals. It means inverse, right? So here we go. In inverse, here's like the technical math definition. Two things are inverses, right? So in this case, f of x is a function and g of x is a different function. Those two would only be inverses if you did composites, right? So f of g of x, and it's just a different way to write f of g of x. You could also write it as, you know, again, f of g or g of f, right? But the other way to write it is like this. So if f of g of x, if you did all of that and it's simplified to just x, and then, you know, if you did it the other way, it would work too. Those would be inverses, right? So that would be like, you know, in the last case, if when we did these, right, if it just simplified to x, those would have been inverses. Obviously they didn't. One simplified to x minus 4. The other one simplified to the square root of x squared minus 4. They're not even close to x. But if they did, they would have been inverses, right? And that's kind of the definition of an inverse. And ultimately, they are just reflections, right? Which we'll get into. So we have the original function is 2x plus 1, right? That's a line, y-intercept of 1, slope of 2, great. If we needed to find the inverse, we'd simply just solve f of y. And if you're not sure what that means, it's basically, instead of f of x, f of y. You just flip the x and the y, and that's it, right? So if this was the original function here, I would flip x and y, and I would say x equals 2y plus 1. And then I would, you know, now I would want to solve for y. So I'd subtract 1. I divide by 2. And I would get y, which I'm going to replace with f inverse of x, because that's how we want to replace the y. We don't want to use y anymore because it's not the same as this y. They're two different functions. But we say f inverse of x equals x minus 1 over 2, right? Or if you wanted to put it in slope-intercept form, that's 1/2 x minus 1/2. Doesn't matter to me, however you do it. Right, and that would give us our inverse. So x minus 1 over 2. From there, if we were asked to graph it, right, you'd want to make an x and y table and then graph them both, right? So that's what we're going to do here. So we had, let me just make sure I did this. Okay. I'm going to make a note about that later. So we had, right, f of x equals, and that original was 2x plus 1. And then we had f inverse of x equals x minus 1 over 2, right? So if we were going to graph those, I mean, you could certainly go ahead and graph those without using a table. You know, I think you'd be okay. But, you know, let's just make a table just to see what we see, right? So the first one's going to be the original. So if I wanted to plot some points for this one, I could plug in 0, I'd get 1. I could plug in 1, I'd get 3. I could plug in -1, and I would get -1, right? All of these points, 2 is going to give me 5, right? You can go on and on and on and on. But the graph is just going to be a y-intercept of 1, right? 1, 3 was another point I found. -1, -1, 2, 5. But it's, you know, it's a line. And we kind of know what that looks like. Now the green one is still going to be a line. And if I wanted to find points from that one, right, I could plug in 1, right? If I plug in 1, I get 0. If I wanted to plug in -1, I would get -1, which is the same point right there. Let's say I wanted to plug in 3. If I plugged in 3, I'd get 1. And if you notice what happens, if I plug in 5, I'm going to get 2. if you notice what happens, these two tables are reflections of each other essentially, but basically the x's and y's are all flipped, right? This one had 0, 1, this one has 1, 0. This one had 1, 3, this one has 3, 1. They both have -1, -1. Technically they are flipped, but you can see that the coordinates are just simply flipped from each other. And so you still get a line, and that's what they look like. And the question below is, it's a reflection over which axis, right? And if you remember from last year, it's okay if you don't, but it is a reflection over the axis, which is y equals x, right? So that would just be a slope of 1, you know, that basically goes right through. It's like a 45-degree angle this way, but you know, it's 1, 1, 2, 2, 3, 3, 4, 4, -2, -2, -3. It's just a line where the y value equals the x value. And so what inverses are, if nothing else, they are simply reflections over the y equals x axis. So whatever inverse function that you have, the inverse of it, right, whatever function you start with, the inverse of it will be the exact same shape. It will just be a reflection, right? So you always want to check those with your answers. Whenever you're solving for an inverse, make sure that it matches the shape of what you originally found, right? And it's very easy to graph. If I ever ask you to graph a function and then graph its inverse, it's super easy. All it is you don't even have to recalculate the inverse. You can simply just flip the coordinates of the original and you will have a graph of the inverse. So it's a very easy question. You just have to know what you're doing, right? Which is the same way of saying if all the x's become y's, that means the domain of the original is the range of the inverse. And then likewise, you know, the range of the original is the domain of the inverse, right? And that's pretty much inverses. Now there's this thing called the horizontal line test, which you may have remembered from last year, right? So, you know, a horizontal line test tells you nothing really about if something's a function or not, right? There's a vertical line test that basically tells you if something's a function, right? So this doesn't pass the vertical line test. So this graph is not a function. But if we graphed, if we graphed a parabola, right? That is definitely a function. It passes the vertical line test. What it doesn't pass is the horizontal line test, which doesn't really mean a whole lot. But what it does actually mean is that if you needed to find the inverse of something that doesn't pass the horizontal line test, you could still find the inverse, but the inverse is not going to be a function, right? If we can imagine, you know, reflecting this over an axis, you know, that's a diagonal line, it would actually end up looking like a sideways parabola, which isn't a function, right? But it still has an inverse. That is still the inverse of it. It's just that the inverse isn't a function. It's not something major. It's just, you know, every once in a while you get a question like that. All right. So what I want you guys to do is you have 7 questions on your classwork. You can skip number 3. Number 3 is something I might need to explain in person. You can give it a shot if you want to, but go ahead and do numbers 1 through 7. And then what I'm going to do is this video is going to end, and then you can start video 2, which is where I'm going to give you those answers and then finish up the rest of the slides.